Good morning. My name is Charles Howard and I'm a retired orthopedic surgeon. And I'm afraid, apart from one semester in Ben Gurion University, I have no connection with geology or earth sciences. So you may say I've got a bit of a cheek coming out with a hypothesis about agate formation, which claims obviously that other well-established hypotheses are incorrect. Anyway, here is the story of how it came about and what came about. It all started as I was passing a crystal stall and noted this agate. My initial reaction was that it was exquisitely beautiful, and it seems, secondly, that a liquid was flowing out of it and then suddenly became frozen in time. But stones aren't liquid, they're solid. I thought, beautiful and interesting. So I bought it and started to read up about how agates were formed. But none of the hypotheses that I came across seemed to fit the morphology, and in many cases just simply ignored many of the features that were present. Firstly, the laminar flow pattern around the escape tubes. You can see how the bands are thinned and elongated due to laminar flow, with the inner layers flowing faster than the outer one, stretching them. It's difficult to see how this could happen during the degassing escape phase, which is thought to occur, if the bands were formed by a self-organization crystallization front or a layer-by-layer crystallization. One would expect to see fracturing or explosion of the agate, and these are never seen. Secondly, the bands have wave-like undulations, and there are also different types of bands. Some are vesicular, some are plain and regular, and some are fluffy with fingers or spikes protruding into the next layer. Thirdly, the impurities, which give much of the colour and beauty to the agate. Notice how they're round or globular, and for the most part attached to the inner surface of the band. What they aren't are facet-shaped, crystal-shaped entities. Fourthly, the surface pits and the effect they have on the underlying bands. The bands are inverted as though some force had punched this part of the bands. As you can see, the central part of the bands are more bunched up than the sides. Sharp angles occur between bands and so produce sectors. And there was one other aspect of the self-organization crystallization front hypothesis which we found difficulty with. That is the claim that many agates consist of thin concentric layers whose thickness, especially in the region next to the wall, increases inward in a regular way, from sub-millimeter to millimeter values. We have never found an agate which follows this regular mathematical pattern. So my physicist colleague Avinoam Rabinovich and I started to think about a new hypothesis. And it seemed to us, from the above, that the bands cannot be formed by a crystallization process, but are present in the sol-gel precursor before and completely independent of crystallization. The undulations, the laminar flow, surface pit inversions and the sharp angles must have taken place while the bands were still fluid. So we did some experiments in which we formed amorphous silica gel from sodium silicate and acid. The results were unexpected and produced morphological features that closely mimicked agates. Firstly, we took a glass cell in which we placed a layer of silicate and on top placed a layer of sulfuric or hydrochloric acid of various concentrations, being careful to avoid mixing. And as you can see here, we got banding. Under the microscope, in addition to bands, advection fingers were thrown out and partially retracted. These advection fingers were remarkably similar to protrusions seen on some of the bands in agates. In other experiments, we noted other similarities between the silica gel bands and the agate bands. In this case, vesicular bubbly bands can be seen both in an agate and in precipitated silica gel. We made a clear, low concentration block of silica gel and left it to dry at room temperature for a day or two. As it contracted from water loss, its surface formed bits similar in size and shape variations as those on agates. We added a small amount of an iron sulfate to the acid before we dropped it into this sodium silicate and looked at the impurities produced. They too closely resembled the morphology of the impurities of agates. We looked at the effect of diffusion without advection by placing sodium silicate in a semi-membrane tube, dialysis tubing, and although we did get amorphous silica gel, we did not get any banding. Macroquartz. This is a major morphological feature which has to be explained. Fortuitously enough for us, in one agate, and admittedly it was only in one agate, we noted that there appeared to be broken remnants of bands and in addition impurities within the large quartz crystals. On polarized light, we could see individual microcrystals of the chalcedony lying within this large macro quartz crystal. To summarize, we hypothesize that the agates arise from a sol-gel silicate precursor within a volcanic vug. Influx of reactive metal ions or acid ions produce advection, which in turn precipitates out amorphous silica in the form of bands. As the lava pre-agate rises, the pressure drops and the material is degassed. Degassing of the spherical sol-gel agate precursor produces contraction, but different parts of it contracts at a different rate, producing A, the sectors, and B, the distortion in the spherical shape which we see in agates. Laminar flow of the bands around the escape tubes, surface pits with underlying band inversions and sectors are produced. At some stage, the amorphous silica is converted to microcrystalline quartz, but the morphology does not allow elucidation of how this occurs. However, Silvestri has shown that, at least in glass, which is also an amorphous silica, this state change from amorphous silica to crystalline banded quartz can occur. We then feel that over a long period of time, water enters the agate and dissolves the inner layers of chalcedony. Again, over a long period of time, these are recrystallized into macroquartz, sometimes retaining parts of their parent bands and impurities. Thank you for listening. We appreciate that our hypothesis of agate formation, based on the morphology and similarities with silica gel, inevitably is incomplete. However, any hypothesis, at the very minimum, must explain the morphology, and we are grateful for the opportunity to present our findings.